Hello, what is up guys? Welcome back to my channel. My name is Tony and today we're going to cover knapsack problems, which is another sub-variation for dynamic programming. And in this video, we're going to cover another 8 problems and which we're going to cover this inside and out to make sure you understand all the details for knapsack. And before we move on, I would really recommend you to watch this video before you actually watch my video. And this is from Stanford as well, and this is going to cover the proofs for knapsack, which is truly great. And before watch my video, make sure you watch this and to get some deeper understanding for knapsack. And let's go over a little example for knapsack, and this is the core idea for knapsack. And here's one of the example, right? So for example, you are a theft. Or let's make another better example. So let's say you are a shopper and you have a bag, a knapsack, and the knapsack can accommodate a weight with 50. And you have different items in the store, and there are 3 items in this case. So the first item weight is 10 and the value is 60. And the second item, the weight is 20 and the value is 100. And the third item respectively, the weight is 30 and the value is 120. And in this case, your bag can only accommodate weight 50, and you will pick the weight 30 and you'll pick the weight 20 in order to get the value 120 and 100, and in order to get 220 in total. This is called a 0-1 knapsack. And in our problem, we are gonna see question raised like you have 1 items can be picked twice, and that could be a different story. So let's say, for example, right, let's change the example a little bit. So if you can pick 1 item multiple times, then picking 30 and 20 does not make sense. So let me pick 30. So I got 120 and I still have 20 left in my bag. So I still can pick another 20 weights. So which should I pick? If I pick 20 from here, I'll get 100. If I pick 10 and 10, I'll get 120 because 60 times 2 is 120. And then I'll get 240 in total. In that case, I'll get 240 in total instead of 220. So by allowing picking 1 item multiple times will change the value, change the eventual results. So in this case, the example provided by Geeks for Geeks is 0-1 knapsack, and keep that in mind. And we're going to talk about the differences in the future slides. So with this question in mind, and let's check the solution. So just like other dynamic programming solutions, we're going to have 2 types of solutions. So one option is by using bottom up, and which I do not recommend for beginner, because for bottom up, 1 dimension, 2 dimensional are okay. But once you move on to 3 dimensionals, the initialization, the transformation function, and if you move on to 4 dimensionals, like it's getting super complex. And start with top down will be much simpler, because all you do is passing the parameters and find out the relationships. So another thing is, when you're building the bottom up approach, you are initialized as a smaller problem, and you want to find the transformation function from the smaller problems and transform that into a bigger problem, and which is counterintuitive. But when you solving this with the top down, which is the second approach, and you are solving this with a recursive function, which you're breaking down the bigger problem into a smaller problem. And in this case, it's more intuitive because we were trained for recursive functions, and that's how we're gonna solve the problems. And let's think about the top-down approach first. So I think the post only provide a recursive function with without cache, and that's why let's just go over this first. So, and the base case is that they initialize the number as 10, right, as n. So we have n items in the bag, so we can either pick the item or do not pick the item. So we pick the max. So let's check the recursive function first. So we only have 2 options, right? We can either pick the item. So if we pick the item, so we call the recursive function again with 1 number left. So we initialize as n items, right? And now we have one less item because we already picked that particular item. And once we pick that particular item, and our weight will be changed by this. So because we pick this particular item, we will minus the weight for this particular item. So for example, let's go back to the example, right? So we have the weight as 50. If we already picked this particular item, we only have 20 left. So we are gonna subtract this 30 from the recursive function when we restart the game, right? So that's how we subtract it. And remember, these two are the only variables that are being changing. So in the later time, when we're gonna cache the value and to store what we already calculated, we're gonna use these two as well. And this is the option number one, right? We are gonna pick the item, or we do not want to pick the item. So we still want to move on to this item because we do not want to pick the item. So let's skip that, and we do not need this item anymore. And we can go back to recursive function without the weight changing, because the weight will not change because we don't even want to use that particular item, and we're done. So this is how we using the recursive function. So there are of course like the different constraints. So let's check one optimization we have. So this is not necessary, but this is one of the optimization. So once we go into a item that weight, the particular item weight is more than the total weight we have. So for example, the total weight is 50 and one item the weight is 60, is already over the total weights we have. The bag cannot accommodate more than the bag can accommodate. So in that case, let's just skip. So if you check carefully, and this is actually the second option. So we do not want to touch the item. So we do not change the weight. So by the time your weight reach 0, or you do not have any items to pick from, in either cases, we're going to return 0 because you cannot gain any value anymore. And that's the entire thing for the recursive approach. Of course, this is a recursive approach and nobody likes it because the time complexity is 2 to the nth power, because each item can either being picked or do not being picked, and it become a tree structure. So we have 3 items, or the weight is 2, and then we either pick or not pick, and once you reach the subtree and the second the next layer, you're gonna have pick or not pick, and it become like almost like exponential. It become 2 to the nth power. So how do we optimize it, right? So if you check the value carefully, and we're gonna have 1 and 1. And 1 was being recalculated, and we have 0 1, we have 0 1. Of course, this is already reached the base case. So but this is not the perfect example, right? But once the tree is being like super big, you have like more than 5 layers, you will see a whole bunch of like the values being recalculated. And what we do is we pick 2 variables that can determine the state, and we use that particular state to cache the value. For example, in this case, it's 1 and 1. So if 1 and 1 is being calculated in this case, why do you recalculate it right here? So we can just use 1 1, which is NW, as the key to hash the value, and we do not want to recalculate the value. And then once we cache the value, when we come back, and we can call back from the value, and then so it saves a lot of the time complexity. It may be confusing once we go over the code for caching, so you'll get it. So it's very simple code. It's like 2 lines for code change, and the rest of the logic will be identical to whatever we're seeing right here, so which is the recursive function. And now okay, so I'm not gonna go over the bottom up, so which is pretty obvious as well, but this is like I mentioned, 1 or 2 dimensionals. But once you move on to 3 dimensionals, you're getting super complex. Okay, so let's go over our slides. We're gonna move on to the 8 problems, and before we move on to the 8 problems, let's go over the 2 things we're gonna see in the future slides. There are 2 types of knapsack, as we discussed in the 0 1 and the infinite knapsack. But there are if you're breaking down the problem into 2 types, we're gonna see 2 types. So the first type is given and constrain and find the max value. And this is exactly what we see in the previous slides, right? From the gigs for gigs, and you are a shopper, you are given a total weight, which is 50, and the 50 is going to be a constraint, and find the max value from the items. Like we got 3 different items, and that's the type 1. And we got the second type, which is given a target, find the corresponding option. So for example, that the question is giving you like, oh, we are giving you a value 240 or 220, and we are also giving you 3 items, just like the previous problem, right? And we want you to pick some items to make up this value. So you pick a value like the weight's 30 and get the value 120, and you pick weight 20 and get the value 100. And as long as you can get 220, and we are okay. And in this case, we don't care about the weight anymore, so which is actually easier, right? So forget about weight, forget about the cost. So there's no more cost. So the second one is actually easier than the first type, and because you don't have the constraints for weight anymore, and all you need is find a whole bunch of like values to accommodate for the corresponding target. So it might be too abstract to talk about this everything in the slides, and let's move on to the actual concrete example, and we're gonna get more understanding. And this is actually let's read the question first. You are given the coins of different denominations and a total amount of money amount, and write a function to compute the fewest numbers of coins and that you need to make up this amount. And if that amount of money cannot be made up by any combination of the coins, and then return -1. So what the question is asking is giving you a whole bunch of coins, and you want to make up this amount. And this is actually the second type, right? This is actually the second type of the knapsack problems. And let's check out a couple examples first. And 1, 2, 5, you want to make up 11. You have a whole bunch of options, right? You can pick 1 11 times, or you can pick 2 5 times and pick another one, or you can pick 5 twice and pick another one. And the question is asking you to calculate the fewest number of the coins. And in this case, 5 plus 5 plus 1, which is 3. We only have 3 coins being picked, and that's already made up this amount, and the final result is going to be 3. But like in this case, the coin we're giving is only 2, and the amount is 3. It doesn't matter how many coins you pick, you either have less than this or you either have more than this, and that's why you return -1, because you can never make up this amount. And you are given these coins, and the amount is 0. It doesn't matter what you given, because the amount is 0. You already have 0. You already broke. So that's why we just return 0. And the last one, the coins 1 and the -1, of course we just return 1. Okay, so with this example in mind, and now like we just think about how to solve it, right? Remember when we solved the last problem, and for almost all the recursive approach, we only care about 2 things. First, base case. Base case determines what the values we are returning, the values that we are hitting the base case in case we are reaching the maximum recursive stacks. Second thing is the recursive function. Recursive function is the main logic. It's how we breaking down the bigger problem to the smaller problem. In this case, we have a whole bunch of coins. For each coins, we can either pick it, we can either not to pick. So that's the main logic. And now with this in mind, so we can move on to the actual recursive approach, right? So if the amount is less than 1, and we don't need anything, so we just directly return 0, right? That's simple. And this is actually the main logic. So this is a Python inner function. So if you're a Java developer or like a C++ developer, so just bear with me in the next slide. So all I want to do is to talk about the main logic for recursive approach first. So remember, if you check this right, so when I pass the DFS, like the function, so I pass the amount, but I call this remain because I use this particular amount to reduce from the higher amount to lower amount. But once we reach 0, and that means like we already fixed the amount. So to the same thing, you actually can start with another variable called the summation, and you start with 0. Once 0 reach to this amount, and then you can use that as a base case too. So it depends on the personal preference. So I use both way for the future slides. So we start with this particular amount. So every time that when we pick a coin, every time when we pick up coin, we reduce the coin amount from the remain. That's how we do. And as long, but if we pick right, if we pick the coin, the weight will be changed. And what's going to be changed again as well? How many times we pick the coin will also be changed, if that makes sense for you. So let's say we have 6, 1, 2, 5. Let's pick 6 first. If we pick 6, and then we're gonna have 5 left, and we go back to recursive function, right? But once we go to the next layer, the total value we have is not 0 anymore. So before we pick anything, we picked 0 coins. But once we pick 6, we will pick 1 coins already. So we have to record that. So that's why we plus 1. If that makes sense. Okay. So with that in mind, and let's go over the total, the overall, right? Let's go over the basic for base case. So if we keep picking the coin and pick the coin, for example, we pick 6 and we pick 1, pick 1, pick 1, pick 1, and pick 5, 1, and it made up this particular amount, and the remain eventually will become 0. Once it becomes 0, we are reaching the base case, and the base case is going to be 0, because once we return from base case all the way to the top, we're going to accumulate this 1. We're going to accumulate how many layers we go, because each layer we pick 1. When we're going back to the top stack, we're going to have 6 and plus 5, 6. So it's going to be 6. So we picked 6 coins in total. Right? So that's the base case for this. But when we have less than 0, what does that mean? So if we pick 6 in the first layer, and when we going back to the stack and we going back to recursion, we pick 1 more time. So the second coin we can pick is, we pick another coin as 6. So we can pick 1 coin multiple times in this case. So if we pick 6 1 more time, we have 11 minus 12, which is -1. So which means you don't need to further pick anymore, because you already overweight, because you are already reaching to 11, and your weight is way more than what we can accommodate. That's more than the target. If you pick another 5, it doesn't make sense anymore, because you already have more than we need. So we just return a the initialized value, which is the infinite number. So why do we use infinite number in this case? Because in the final result, we can check. We have 2 options. Either the value does not change at all from the recursive function, or we are reaching this guy. In either case, that means like we are not reaching the correct results. But as long as we can get anything from this, we will have a valid number which is less than the infinite number, which is either something plus something. That number will definitely lower than the infinite number, and that's where we return the results, and that's the main function. And now let's come back to recursive function one more time. So with the base case in mind, once we understand the base case, I think it's also easier to understand the recursive function. The recursive function, like we mentioned, we are given a total weight, and each time we can pick a coin or we can move forward. So when we pick a coin, we can pick any coin. We can pick either 6, or you can either pick 1, or we can pick 2, or we can pick 5. So let's go and pick 6 first. We can pick 6 first. The coin will loop to 6, and you will go to the DFS. If you pick 1, you will go to the DFS wall. So at each item, we will go throw a thread into a subtree. So the subtree will be start with 6 and pick 1 and pick 2, 6 pick 1, 6 pick 2, 6 pick 5, and 1 pick 6, 1 pick 1 pick 2, 1 pick 5, 2 pick 6, 2 pick 1, 2 pick 2, 2 pick 5, something like that. So it will become a massive tree. And how do we cache that? And the way we cache that is by using this. So for Java developer or C++ developer, you do not have this, but in Python will use the input as a hash key to store. So it's the same thing to put a code like using a hash map. If the remains in the hash map, you bring back from the key, and at the end of here, so you store that into the hash. So it's the same thing like that. But we can just treat this as a recursive function. We know this is a working solution, and putting this will make it like n square time complexity. But let's put a manual hash. Okay. Now this is the, if you're like C++ developer, so you understand this actually. Same thing. So we have the corner cases to deal with. We call the recursive function, and then for each coin, we're looping through, and then we subtract the weights from the total weights, and then we plus 1 for each layer. And we have the base case. When the remains 0, that means we already reached the target, and when remains less than 0, that means like we will never reach the target because we already overweight. And that's the key thing, right? So if the remain is already being calculated, and then we just bring back from the cache, so we cache it, right? And once we finish the calculation for this particular weight, and we put the weight into hash map and store the values that we calculated, and in the future, so when we want to bring back the value, we just bring back from here. And that's the entire idea for the problem 1, and that's gonna be the templates for the future problems as well, for a lot of the dynamic programming, especially when you use top down. And this is going to be the templates, and you would know beyond the base case and recursive function. And let's check the next one. So coin change number 2, you are given the coins of different denomination and the total amount of money, and write a function to compute the number of combinations that made up this amount. And you may assume that you have infinite number of each kind of the coin. And it's the same thing with the last question, and the only thing changed is the return function. So I would say the most of the recursive part will stay the same, but the only thing different is the base case, because the base case is the question is asking you how many ways you can make up this amount. And in this case, let's check one of the example, 1 to 5, and you have 5. You can pick 1 5 times, and you can pick 2 once, and 3, and made up the rest of the amount with 1. You can pick 2 twice, and made up another 1 with 1, and you can pick 5 once, and you can have another way to make up this amount. Alright, so for each coin, we still have only 2 options. You can either pick the coin or not pick the coin. So let's write it this way. So we still like writing the recursive function right here. So the amount is still gonna be the amount. It was the remain. So now like I just named that as an amount. So let's check the recursive function first, right? So we are given this amount, and for each item we pick, we can either pick the particular coin, or we can either skip the coin. Now, like let's go over the header first actually. So we passed the weights. We also have the index right here. The index stands for where we up to. So the index starts with 0, and each time we're gonna increment, and by the time the index go over the entire coins, that means we already picked all the coins. we are already leaving all the choices on the table. We do not have any options anymore, and that's where we hit the base case. So that's where we hit the base case right here. Okay, now we check the recursive function. For each item, like where we up to, right? For the I, we can either pick this coin, or we can leave it on the table. If we pick this coin, that means we reduce the amount. That means like we already made up some of the amount, so we just subtract that from the recursive function. That makes sense. And so what confused me in the beginning is why we have I right here. The key idea is, remember the question is saying we have infinite number of each kind of coin. So which means we can repick this particular number. For example, right here. So if I pick 1 in the first round, in the second round, we only have 4 weight left. I still can pick 1. So that means like I stay the same. I still can pick the 1. I can pick 1 forever. That's the first option. We pick these particular coins. But could I pick 1 3 times and move on to next one? Yes, I can pick 1 3 times. I can take 3 times and move on to next stack, which is do not take. Do not take means I only increment this. I don't care 1 anymore. I can move the index to the next one. So that's why my I will +1 right here, because I don't want to touch this part. I don't want to touch this item. So if I do not touch this item, I would not change my amount. So that's why my amount is not changing. I do not put this into my bag. So I do not put this into my bag. So that's the 2 cases we have. So we either take it or not. So for each options, we'll generate how many ways we have. And that's where we come back to the base case. And then we, for the return value, we're gonna take the summation. So we either take it or not. And we take all the ways. And we come back to the base case. So when the amount reach 0, that means we have at least 1 way. We have 1 way to make up this amount. That's great. And we just return 1. But when the amount is less than 0, we do not have any ways to make up this amount. So we return 0. Or we do not have anything in the coin. We still didn't reach here. So because we already checked, we did not reach here. So once we come to here and we see, oh, there's no more coins, we are still not go over this amount. Yeah, we are not still not reaching this amount. We don't have enough coins to make up this amount. We also return 0. And plus the recursive function, this is the perfect explanation for this problem. Okay, let's go over another approach for this the same problem. So by using loop, right? Okay, so still we have the base case right here. This is actually the corner cases. So when we do not have any coin, and if the amount is 0, that means we can we already broke, and the required amount is 0. So that's why we have 1 way. But if not, so we're gonna return 0. And in this time, we're gonna sort the coin. So why we wanna sort a coin? So I'm gonna talk about it in here actually. So just remember we sorted, and because we're gonna do some optimization, so it's right here. Once we sorted, we're still coding the recursive function. This time we just manually cache everything. So we pass a hash map right here just to cache the values that we already calculated. The last problem, we still using the Python trick function tools RU cache to cache, but now we're just gonna manually cache it. And what are the variables, right? So the index where we up to, which items we already being picked, which items are haven't been picked. So this will be the positions, and the amount will be being reduced whenever we pick a coin. And this is changing as well. These 2 keys represents the unique states for each state that we already being computed. And whenever we already finish the compute, and we just cache the value from here, and whenever that these 2 state which represents the unique state were being computed, we can just bring back from the cache. And that's the standard approach for a memo with the cache. And so we're gonna put it here, and the rest of the story will remains the same as a DFS. So when we reach the amount, when amount equal to 0, that means we already reached the amount, and we return one way. That means like we already have one way to represent the target. We already have one way of coins. The coins we pick can make up this amount. Perfect. So that's the base case. And now we are going into the recursive function. It might be slightly different, so I'm gonna discuss the detail. So we are starting from the index, which is 0. So we are starting from right here. So with 1 right here, I can pick from 1. If I pick 1, the next layer, I can pick either 1 to 5. If I pick 1, the next layer, I can pick 2, 5. If I start 1, I can pick 5. So, and then if I move on to 2, right? So that's only when we start with 1. If I start with 2, does it make sense to pick 1? So if I pick 1 and 2, or 2 and 1, that's the identical approach, right? That's actually identical. So if I already covered this part, if I already have 1 being picked and pick 2, so it doesn't make sense to have 2 and pick 1. So that's why the index right here is I. So I start with the index. I started with the index from here. And the next round, I will allow you to either start from here or start from here or start from here, because I already tried out every options. And that's what the recursive function means. So whenever we pick I can pick any coins. I can pick either from this guy. So the recursive function will go over. I can either start with this guy. I can go over, and I can either start with this guy, and the recursive function will generate the subtree. And that's how we do it. So that's the recursive function. So slightly different with the previous approach, but the key idea is a little bit slightly different. But the core idea is the same. And let's talk about these two lines. So when you pick a line, when you pick a coin, that the weight is already bigger than this. So when you have the total weight minus the coin you pick is less than 0, that means like your current coins weight more than the bag can accommodate, you just break. And that's why we sort it, right? So for example, you have 1, 2, 5, 6, 7, 8, 9, but your total weight target is 5. It doesn't make sense to pick 6, 7, 8, 9. So you can just skip from here, and that's why you have the break. And it saves a whole lot of time to go through DFS. And that's one of the optimization for this particular part when you sort it. With this in mind, now we already go over the 2 approach for coin change number 2, and let's move on to another question, so which is exactly the same as this. So let's check the question. So given an non-empty array nums and contains only the positive integer, find if the array can be partitioned into 2 subsets and such that the number the sum of the elements in both subsets is equal. Okay, so the question is asking, if you are given a nums, a whole bunch of numbers, can you partition this into 2 subsets? Actually, the question is wrong. So this is not set. This is a subsequence. Set can only be distinct numbers. So it should be, the question is asking if you can breaking down the array or the list into 2 different subsequence, and to make sure the summation for each subsequence is the same. Can we do that? So when you see this question, so how do we translate this problem to whatever we already know? It's actually simple. So the question is asking you, can you breaking down the problem into 2? Can you breaking down this array into 2? And to make sure that the 2 are the same, if we can only pick some subsequences, some subsequence, just to make up the half of the total, that means the another half will also be the same. Isn't that right? So if we know the total sum is 22, we only need to make up 11. if we know the total is 30, we only need to make up 15. If the total is 31, what do? We just directly return false. It doesn't make sense to start with. When you know that your total is 31, when you divide it by 2 is 15 and 16, you cannot achieve the goal in any place. So you can directly save your time to return false, and that's one of the optimization. And then you know the total is 30, and there's a possibility to make up 15 and 15, and that's where you move forward. How do you move forward? We know we are gonna move breaking down to 15 and 15. So forget about another 15. We just care about the first 15. We pick some numbers can make up 15, and the rest of the numbers can make another 15. That's the approach for this, and that's how we translate it into the problem that we know. Okay, let's go over the code. So we're gonna calculate the summation. If the summation divided by 2 does not equal to mod 2 does not equal to 0, that means we have the cases with the 31 breaking down to 15 and 16 doesn't make sense. So we just directly return false, and we sort the array, just do some optimization, and then we have the memo and divided by 2, and then we're gonna count the stacks for DFS, and we still have the two variables, right? So one is the index and one is summation, and sometimes you can use the total amount target to subtract. And in this case, I have the summation, which is one more variable. Once the summation will reach the target, and we return true, and that's how we do it. But you could save this variable by just using the target to subtract, just like the previous case. And in this case, I have different approach, but the key idea is the same. And then we use target equal to summation divided by 2. That's the target. So if we can reach this, and we already succeed, and we still have the base case and also have the cache values. So when the key variables, the keys are already being calculated, and this represents the unique identification for each state. And if the state was being calculated, we just bring back from the cache. If not, we just keep moving forward. And the base case is when, like we mentioned, the sum equal to the target. That means like we already reached the target, so that means we can split one of the subsequence into the target, and which means the another half will be true as well. So that's great. So we just return true. So if the summation already reach out, go beyond target, so return false. That means like we have the values more than what we need. And we also start from that's just like the second approach from the last coin change to problem, right? We start from this index, we can if we start from here, we can move back. But if we start from here, we do not want to move forward, because one already pick 5. For 5 does not necessarily pick 1, so that's why we only move forward, and we go from index all the way to the nums. And each time, so we want to have because we cannot because we cannot pick a number multiple times in this case, and that's why when we doing the DFS, we'll have I plus 1. So I means like the summation will plus if we pick this item, so we plus this the nums I, right? We already plus that. The next round, you cannot pick this particular value anymore, so that's why you will have I plus 1. So I do not ice right here. I do not want you to touch this part anymore. So just go ahead and move forward. And if the value can be succeed, and then we just return the value as true. And if not, if we tried everything, we tried start with this guy, start with this guy, start with this guy, move on to others, like still does not succeed, and we just return false. And that doesn't make sense because we cannot succeed. So we just return false, and we just return the final value from here. All right, so let's check another approach, right? So still, like, we have the target and mod 2, you know, like if it does not equal to 0, so we just return false, and then the target divided by 2 is gonna be our target. So same thing like what we described before. So in this case, I just use one variable instead of having some. And one of the things we have right here is the visited. So I think it's one of the optimization, because when we trying out all the numbers from here, we do not have the optimization. And we could reuse some of the numbers, but in this case, like if a number already being used, we're just using the array to represent the entire numbers array. If the numbers being picked, so we just put that as true. It's more like a backtracking. And then once we finish the using and we turn it back to false, so that means like we haven't picked that. So everything else is the same. Everything else is the base case is the same, and the only optimization we actually have two optimization right here. So one type of optimization, like we mentioned, is using the visited array to checking if the numbers are already being picked. If the number is already being picked, and we just continue, we don't care anymore because we already used U. So we don't double use a coin, double use a number. So if not, so we put that particular number as true, and we backtrack right here. And in the middle, we still call in the DFS each number. But in this case, like each time we only move forward by one value, right? Still right here. And then so this is actually the optimization we have. So if the previous value, we didn't pick the previous value, and this value is also equal to the previous value, does it make sense to pick this particular value? Because we don't need the last value, and the last value wasn't being picked, and this number is equal to the last value, and it makes sense to skip this as well. So that's the cases when you have 1 2 2 2 2 1 100 100 100 and something like that. And so it doesn't make sense to recalculate those values. So we have the optimization. But my favorite approach is still this one, which is much simpler. And when I compare the speed, it wasn't significantly slower. It was a little bit slower. So yeah. Okay, let's try a similar problem again. So 473 matchsticks to square. Remember the story of the little match girl, and by now you know exactly the match sticks that a little girl has, and please find out the ways you can make up the square by using up all the matchsticks. You should not break any stick, but you can link them up, and each matchstick must be used exactly one time. So this is also 01 knapsack, and your input will be several matchsticks that girl has represented with their stick length, and your output will be either true or false to represent whether you could make one square using all the matchsticks the little girl has. Okay. So we have a whole bunch of like matchsticks, and each matchstick has this length. So can we make up a square? Square means you have 4 length, and the parameter will be breaking down into the equal sum. So what it means is that for it, the side of the square will be identical, right? And so 1 and 1, you cannot break 2 into 1 and 1, but you can make up, you can link them up. So 1 and 1 will be equal to 2, and you have 2 2 2 and 1 1 1 can make up 2. So in this case, you can make up a matchstick, and you have 3 3 3 3 4. And 3 3 3 3 is perfect, but when you have 4, like you cannot make a square from the matchsticks. And this problem is actually almost identical to the previous one. So the previous one, you're gonna find all the numbers, and you're gonna break this down into 2 subsequence and make sure the 2 subsequence are identical. But in this time, you're gonna break the entire array into 4 different subsequence and make sure the subsequence are identical. So slightly tougher than previous one. In the previous one, when you breaking into 2 different parts, you know one part and you know the another part. But in this case, if you know one part, you still can't determine the global. You need to at least know 3 parts. So when you calculate the 3 parts, it's the same thing to calculate the 4 parts. So it cannot save you like any process. In this case, we're just gonna use an array to calculate all the 4 parts. So let's go ahead and check how the code looks like. So in this case, we're still checking the sum and check the modular. So if you mod 4 equal to 1, that means like you have something left, and you just return false. Otherwise, like you just keep going for the DFS. And in this time, we actually want to sort reversely. So the reason is that, for example, we have 3 3 3 3. Let's say 3 3 3 10,000. So the 10,000 is way too long as a side of the square, and it doesn't make sense to put it there. So as long as we have there, so we put that as first, and then that could be easily reach the base case, and we're just breaking out from there. So that's a easier approach and for optimization to save us some time. And now, okay, so once we have this optimization, and then we check the base case. So let's check the input value first. So input value will be the results. The results will be 4 elements anymore. So each element represents the side of the square. So the first square has the length, and second square has length 0 initially, and the third length has third side has the length as 0, and the fourth side has the length 0. And we initially, like, we pick the value from the very left, so the index start from very left, and pick one value at a time to move forward. So that's the position or the index. And the summation divided by 4 will be how many it will be the target value. So each side will have this target value. So because we already pre-check that it can mod for, and okay, so this is gonna be the target, and the base case will be once the position reach the end, we do not have any matchstick to pick from, and then we check the results. If the results is 0, equal to 1, equal to 2, that means the first 3 lengths are the same. That means the fourth one, you can put the fourth one right here, but like once you know 3, you'll know the rest because you know the total already. Okay, so in that particular case, so we just return true because we already succeeded. If not, and we also reach the end, that means we return false. We cannot succeed in this case. Okay, so with the base case in mind, and let's check the recursive function. I feel like the recursive function is much easier this time, just like the former problems, right? Okay, so we're gonna loop like this 4 times. So 0, 1, 2, 3. So each time we're gonna try out every options we have. So we wanna put the first position is right here. We're gonna put the first matchstick into results 0, results 1, result 2, result 3. We're gonna try out everything. We put it here, we'll put it here, we put it here, we put it in the next round. When we put it here, when we put the first matchstick right here, we could put the second matchstick right here, or put the second one right here, and blah blah, keep going forward. And that's how the DFS works, right? Okay, so that's the DFS part. And we have one optimization we have, so which is when your current side plus the current length of the matchstick is already greater than the target. It doesn't make sense to move forward because we have the constraint for each length. If your current length plus the length plus the matchstick you are about to put on this side is already over the target, it doesn't make sense, so we just continue. If not, if you can still put that particular length or matchstick onto this side, we just put it there and we backtrack. So make sure there's 2 parts. You can put it there, you can backtrack, and in the middle we just do the DFS. So position +1 means like we already picked this matchstick and we're gonna move on to the next one and try out everything. So only if one of the option will make it work will work. We only need one option. You want to see the future of like 10,000 probabilities, and if one of the option will work, it will work. If all the options, if all the choices you have, like right here, does not work, and then you return false, and that's for this problem. And let's move on to the next one. So the target sum. So I think from here, like when you read the question, so you'll realize a lot of the questions are pretty similar, and same thing with this case, right? You are given a list of non-negative integers a1 all the way to an and a target. So we also given a target and s. Now you have 2 symbols, plus and minus for each integers, and you should choose one from the plus or minus from the new symbol, and find out how many ways to assign the symbols to make the sum of the integers equal to the target sum. So it might be confusing at the first glance, but if you read the question carefully, so how do we translate this particular question into something we already know. Okay, so the question is asking, hey, you have a whole bunch of numbers and you have the target sum 3. It looks familiar, but you know, the plus and minus is confusing. You know, plus sign and minus sign it's not so obvious to translate to code. Of course, it's not obvious to translate to code. So we need to translate the problem to something we know. So how do we translate it? So think about it, right? We have plus sign for some of the numbers. We have negative sign for some of the numbers. So we are picking a particular number and we want to assign this particular number into either to one of the group or the another group. We don't have two groups, either plus group or minus group. So why don't we just try out everything and we cache the value, and that's and made up this amount, right? So whenever we made up this amount, how do we made up this amount? We're using base case to cache it, right? So of course, so that's how we translate it, and then the code becomes self-explanatory. And we have the memo right here. So we have the position and the summation start from 0. Of course, you can also have the target to subtract the value, but in this case, I'm not touching the target. So you can tell that the target is not subtracting anything because you have the summation right here to build up. And once we reach the target, and we just return 1. Okay, so that's the base case. So in this particular case, and we have the position is moving and the summation is moving. So once both value as the unique state represents the unique state is already being calculated, we just bring back from the cache. If not, we go over the base case. So the base case is pretty self-explanatory, just like the before. And we start from the 0 index, and once we reach out to the final index, and we're gonna check if we have the summation equal to the target. So if the summation equal to target, so we're bingo, we reached the target, exact the target. So we are returning one of the options. So we are calculating how many ways to assign the variables to make the to make the summation equal to the sum target, right? So isn't that just sounds like the second coin change? Okay, so once we reach the target, we return 1. That means like we have one way to make up the target. So if not, like either less or more than that, so we return 0. That means like we have 0 ways to make up this amount. Okay. And for each position, we're gonna plus 1. That means like we already picked this particular coin, so we're gonna move forward to the next coin. And that's the fun part, right? So for each coin, so we can either plus this coin, that's the plus group, and we can either assign this to minus. So just like the coin, right? We can either take it or not. But when you take it, you plus the value. But when you do not take it, you do not change anything. But in this case, we have two groups. So you either plus, when we do not have the not taking anymore, not taking option. We cannot not take it. We can only minus it. So that's why we have two different groups, and we make the summation for each of the two groups, and then we cache the value and then bring back the value and recalculate it by using the recursive function. So bingo. So that's how we solve this question. So you will see a whole bunch of a problem like this, and almost like identical to this problem. Okay. This is actually one of them. So lost stone weight, number 2. So we have a collection of rocks, and each rock has a positive integer weight, and each turn we choose any 2 rocks and smash them together. And suppose the stone has a weight x and a y, and x suppose like x is less or equal to y, and the result of this smash is x is equal to y, and both stones are totally destroyed. So you are smashing 2 stones together, and if they have the same weight, that means they're gonna be totally destroyed. So for example, 1 and 1 right here. If you smash 1 and 1, the weight will be disappeared. But when you smash 4 and 8, so what's gonna happen? So if x is not equal to y, and the stone of x is totally destroyed, and the stone y will have y minus x. That means like when you smash 4 and 8, 4 will be disappeared, and 8 will be remained as 4 because we being consumed by this particular stone. Okay, perfect. So given this question, so how do we calculate it, right? So if you think about this problem really carefully, and I would say this problem is actually identical to this problem. So how do we do it? How do we translate it? So the way we translate it is you wanna pick any 2 stones. You're gonna smash them. when you smash them, you have this particular number as positive, and you want to have this particular stone as negative. So because when you're smashing them, you're subtracting them, so which means you are assigning the plus sign for some of the stones, you are assigning the minus sign for some of the stones, right? So you are assigning plus and you're assigning minus, and the only difference is in this case we don't have the target sum anymore. So the results is gonna ask you, so the question is asking you to return the smallest possible weight of this stone, and the weight is 0 if there are no stone left. Okay, so the question is asking you the smallest possible weight left from all the smashings, and we're gonna do this with the base case. So the base case is gonna do this part, and the rest of the story will be identical to the previous one. So you know, like we have the initial position, which is 0. We start from the first index, right? The position from the first stone, and for each stone we have 2 options. So one option is we're gonna assign to the left, one option is we're gonna assign to the right. We're gonna assign to the left, we're gonna assign to the right. Now in the end we're gonna smash them. So we assign this guy as a positive, we assign this guy to the negative, and we smash them, and we take the absolute value, because we don't know which one is positive and which one is negative. And it could be this guy, the winner takes all. The winner, whoever gets the more value will be the positive. So we don't know, we don't care, and at the end all we do is take the absolute value for the subtraction. Okay, so that's how we translate to the previous problem. We still have the 2 groups, the plus and minus, and the only difference is like the previous one has the plus and minus, and this guy has, we could also translate this to plus and minus, but in this case I just distinguish them as 2 different groups, and the first group will have this value, or the second group have this value, and this makes more sense, and the code looks much cleaner. Okay, so form the largest integer with the digits that add up to target, and given an array of the integers cost and a integer target, return the maximum integer you can paint under the following rules. The cost of the paint a digits is I plus 1, and given the cost I and 0 indexed. So okay, this is 0 indexed, and the total cost used must be equal to the target. The integer does not have digits 0, so we do not have 0, and since the answer may be too large, and return it as a string. If there's no way to paint any integer given the condition, return 0. Okay, so this particular question is actually 0, 1 knapsack. We have a total weight. This is the type 1, right? In the first slide, we have two types of knapsack. The second type is given a target value, and we are not made up this value. That's the whole bunch of questions we did before. And the first type is we are given a total weight, which is the target. This is the total weight we have. And we have a whole bunch of weight, right? The items, and each item has a weight. The weight is cost. So each time we pick a number. So this is 0, this is 1, 2, 3, 4, 5, 6. Oh, I'm sorry. This is the cost is 0 indexed, but the actual value is indexed by 1, because we plus 1, right? So if we're gonna pick a number 1, the cost will be 4. Pick a number 2, cost will be 3. Pick a number 3, cost will be 2. Pick a number 4, cost will be 5. Pick a number 5, the cost will be 6. Pick a number 6, cost will be 7. We pick a number 7, the cost will be 2. And that's the whole point of the story, the question. So we have a value. Value is 1, 2, 3, 4, 5, 6, 7, 8, 9. And the cost will be 4, 3, something, 2, 5, blah, blah, blah. Okay. Now, this, I don't have to beat the dead horse, because this question is exactly the same thing as the 0, 1 knapsack. And the only difference for this question is the transformation function, which is the recursive function. So when we add up the value, that's the only difference we have. So let's go over the solution. So we have the memo to cache the results, and we have the target. In this case, we don't have the sum anymore, so we just use the 0 as a position, and with the target value as our weight to reduce from. Okay, we have I, we have target, and you're gonna, so these two still variables are gonna still use as a key to cache the value. And once we're being calculated, we just bring back to the cache. So once we finish computation, we store this into the cache. Okay, so that's the standard. Let's check the main logic, right? So the base case. So when target equal to 0, that means like we already reached that particular amount, so we don't have any more ways to pick from. So perfect. So we just return 0. And once we reach the end or the target less than 0, and we still haven't reached the target yet, okay, perfect. So go screwed. You've been screwed. Okay, perfect. So once we have this two base case, right? And now let's think about the transformation function. Oh, I'm sorry, the recursive function. For each particular number, we can either take it or not take it. If we take it, oh, by the way, yeah, so if we take it, yeah, by the way, sorry, so I forgot to explain, right? Each number can pick multiple times. So, okay, so I think they didn't mention that into the question. So, but in the example, they mentioned that you can pick a number multiple times. Okay, so when you take this particular number, you gotta pay the price. So the price is gonna be the cost for this particular position. Okay, perfect. So we pay the cost, and we're going back to the recursive function. So what's the reward we got? The reward we got is I plus 1, because that's 1 indexed. Is I plus 1 because it's 0 index, and we want to start with the 1 for the values, so that's why plus 1. That's the value we got. But for example, in this case, if we pick 7 in the first round, and then we in the second layer we pick another 7, if we take the summation, that would be 14. Okay, that's not the right value. That's why we'll times 10. The first round we pick 7, the second round we pick 7, but 7 and 7 will form 70. So that's why we'll times 10 for the last round from the first layer. In the second layer, when we have 7, it becomes 7. And the third round, let's pick another 3. And the total 77 will times 10. So that'll be 770 plus 3. And just make sure that that part is not traditionally think about, and this is kind of unique for this particular problem. But yeah, this is the tricky part. But once you get this tricky part, everything else is being simple, right? So all the base cases, all the recursive function is the same except this part. And if you do not take it, you just move forward. If you take it, make sure you are not moving forward for this index, because you can still pick this particular number. Each number can being picked multiple times, and you take all the summation, how many ways you can pick. Okay, so that's how we solve this problem. All right. Okay, so let's do a super complex problem. I think this is gonna be the last problem, if I'm correct. Okay, perfect. Yeah, so this is gonna be the last problem, and to summarize the entire slides, and this is actually a really tough one. So the question is asking splitting the array with the same average. In a given integer array, we must move every element of A to either list B or list C, and B and C initially start empty. Return true if and only if such a move. It is possible that the average value of the B is equal to the average value of C, and B and C are both empty. Okay, so we are given a nums, a whole bunch of numbers, and we can split array into 1, 4, 5, 8, and 2, 3, 6, 7, and both have average 4.5. So you want to split the array into two subsequence, and you want to make sure each subsequence have the same average. So for now, like, they don't want you to have the exact same summation, but now they want you to have the same average. How do we do that? So there's a little trick that I'm gonna show you guys next slide. So when you have A divided by B equal to C divided by D. So let's say A is the summation. A is the summation for the global, right? A is the summation for global. And B is the length for a whole bunch of items. For example, you have like 100 elements. B is gonna be 100. A is gonna be the summation for the 100 elements. And C is gonna be, let's say you pick first, you divided this entire array into half and half. The first half has like 40 elements. So C is gonna be the summation for the 40 elements. And D is gonna be 40. So if you divide it by this, you calculate the average for the global, and you calculate the average for the sample picked sequence. And you make sure they are equal, right? Okay, if that makes sense, and let's translate it into our code. So this is the reason that this problem is super complex is by using the traditional approach, and this solution will be TLE, time exceed, time length exceed. So but I'll still go over the traditional approach first before we move on to optimal solution. And we have total length. The total length will be B because we are using the total summation divided by total length. The total summation will be A because we are using A divided by B. So we're going to using total summation because we are sum the entire array. We're going to use total summation to divide it by the length of the global array. So A divided by B. And for each value, we are start accumulating. We want to find a subsequence that the current summation divided by current length of the subsequence. And we want to use C divided by D. If that particular sequence is equal to the average of A divided by B, that's perfect. Okay, so now we understand total divided by N equal to current sum divided by current num will be satisfied the results. And if you know programming 101, you probably realize, wait a minute, so division will have precision issue. That's not good. So, and we will not translate and this division into multiplication. And that's how we do it. So A times D equal to B times C. So do some algebraic. I memorized this part back in junior high, but you can derive this from this equation. So we'll get this A times D and equal to B and C, and these two equations are identical. Okay. Once we have these two equations, and we can move forward with our. This is only hard part. When we actually solving the problem, and you have to derive this during the contest. Okay, so we want to calculate the total length of the array. We want to calculate the total summation for the array, and we sort it and we pass the index. So there are three indexes we want to pass. The first index is going to be the position of the array, so where we up to, and we're going to have the current summation and current num. Current num stands for the length of the subsequence we picked. So this is actually the equation, right? So the total summation A times the current num will be equal to the total length times the current sum. So once this was being satisfied, then we return true. If not, and we have no numbers to pick from, we return false. That's more like a self-explanatory as a base case. And we have two options. One option is we can either pick it or we can not. We can either leave on the table. If we pick the value, so the total num will be +1 because we pick one more number for the subsequence, and the subsequence length will be +1, and the subsequence summation will also plus the value for that particular element, and the index will move forward. And if we do not pick anything, we'll still move forward. So if any of the options can be succeed to reach the base case, we'll return true. if none of them cannot be succeed, we return false. Unfortunately, this approach will be a TLE. So let's go over the optimal solution that can pass the test. So what's special about this optimized solution? And we can check the loop right here. So we are looping through the number all the way to the half, and if the total times num mod the n, so which is right here actually, the total times num mod this particular number, and if we mod this number and we cannot get 0, that means we have one extra outlier. If we have the outlier, we don't even have to continue. We just skip the DFS. That saves us a lot of the time. But if we could continue, and when we divide it by n, that current sum, that particular summation, will be our target. So we did translate this unknown problem into something we know. Now we just find a target. So this is our current sum, and this is our current num. We need to use this this length of the num to make up this sum, and this become easy, right? So we have the base case, and if the current sum and current num become 0, that means like we reach the target, but we have to reach this target at the same time. So if we do not have any value to pick from, we return false, and if only one of them being achieved and the other one does not being achieved, and we return false. And same thing right here, so we either pick it or not, right? So this is where we pick what that particular number, and we have the index move forward. And this is actually one of the optimization. So when the two numbers are identical, we just keep going. It doesn't make sense to pick. It doesn't make sense to add up. It does not change the average value. So we just keep moving forward, and it's one of the optimization. And this is how we do not pick it. So we pick or not pick the particular number. And if none of the options we have does not succeed, we just return false. And that's a good summarization for all the knapsack problems that you need to know. And when you see the new problems, I hope this will be a good examples for you. And if you like the video, and please subscribe, and I'll see you in the next video.